Good afternoon, everyone. Chairman, thank you. My talk is on eutectic trimming of the polysilicon microhemispherical resonating gyroscope. So it's exactly the same project than Cornell was just talking previously. Gyroscope, just to tell you what it is, you all have one in your pockets in your cell phones. So if you look at, like, for example, the iPhone 4, you'll see this kind of, how does this work? Like here, you'll see a gyroscope. It's in this package, it's in this part here. And when you open this, you see this device. So you have a MEM resonant gyroscope. So the resonant gyroscope, as explained in the previous talk, but I have to go over it again for my talk. You have a drive mode here, for example. And as you apply your rotation around the device, then you have the creation of a correlative force. And the drive mode is going to be coupled into a sense mode. So you have one mode at 0 degrees, and you're going to have your sense mode at 45 degrees for VM2 mode, but you could have different modes. We are working on the Hamelin program where we're trying to bring the uHRG, the Hemispherical Resonator Gyroscope, into a miniature version. The two modes that we saw, when they're fabricated, in theory, they should be have the same frequency. In fabrication, mass imbalance, stiffness imbalance are going to make the thing such that the frequencies are not going to be the same anymore. So your drive mode and your sense modes are going to be mode split. And it is good to work in the mode matched conditions because the total signal-to-noise ratio is better when it's mode matched than when it's not mode matched. So to do that, we do an operation that we call mode matching, and we bring the two resonant frequency on top of another. There are two ways of doing things in literature. You can do it at once, like after fabrication, you take your device and you mode match it. Now, when you take your device and you put it into an iPhone or you put it into a spaceship, it becomes too costly to take it out and rematch it if the frequency split is there again. So you have a second procedure called tuning, where you actually, in real time, you take care of that frequency split. So there's trimming and tuning. And our technique is one more in the trimming technique that exists right now in literature. The frequency of resonance of a device that you can see here depends on two parameters, the effective stiffness and the effective mass. So if you modify one of those parameters, or both of them, you can modify your frequency. So most techniques are on mass modification. For example, at UCLA, McCloskey's group is modifying this gyroscope by adding magnets. So this is a large-scale version of a smaller-scale version, and you can add those magnets and you modify the mass at given locations, and they can test their algorithm like this. Other groups have, for example, looked at this kind of device. It's a simple resonator in this case, and they're putting gold patterns on it, and they put a current that flows through the resonator. The current is going to heat the resonator, and you're going to have diffusion of that trimming material inside. And when it does diffuse, you have creation of new bonds. So those dots can be aluminum or gold in their paper, and this is polysilicon. And what happens here in this location, you're going to have a formation of a new material. It's going to be gold silicon or silicon aluminum eutectic. And that material has a different stiffness than the silicon before. So we are modifying, they modified the stiffness, and hence they modify the frequency. Our technique that I'm presenting to you today is actually in the same idea than the one I just talked to you. We're looking at stiffness modification, but instead of flowing a current where the heat is being created depending on the geometry of a device, not how you really want, we are using a laser to locally form those eutectic bonds. In this case, it's not geometry dependent. It depends on where the user is aiming his beam to melt the material. So for our techniques, we basically have two components that are really important. The first one is laser heating, to have this local choice to be able to move around the device. And the second, we need an array of trimming spots, and I will go into more detail about that later. The good thing about our technique is that we're looking at stiffness modification instead of mass modification. So for the uHRG, for example, most groups are looking at modifying the mass around the rim, where we're looking at modifying at the post. And this gives us the possibility to do modification of the mass or of the stiffness. Hence, we're having a bigger trimming area. Finally, because we have a laser, we can have a digital and automatic process. I'll go into more details. Also, compared to, for example, mass ablation, our laser has a real less constraints. We don't need it to be as large, because what's really important is not the size of the laser. What's important is the size of the gold spot that is really diffusing into the silicon, and that's creating those eutectic bonds. So if a laser beam is bigger than the gold, it's okay, because what depends on the size of the gold spot that's diffusing in. So a bit about the physics behind it. What we're really using is called eutectics. And for example, gold silicon from a eutectic, and you see here's its phase diagram. So this is here the temperature, melting temperature of gold. Here the melting temperature of silicon. As you can see, a given composition of the two is going to melt at a lower temperature than the melting temperature of gold and of silicon. So if, for example, you have your laser and you heat your device locally, well, if you're not touching your target location, you're not going to melt your silicon and you're not going to melt your gold, because their melting temperature is above that temperature. Again, as I said, if you look at this graph here, you're going to see that aluminum silicon, the Young's modulus, is actually smaller than the Young's modulus of silicon that was there before. So if you form a eutectic aluminum silicon, the frequency is going to be actually lower than what it was before. And if you have, for example, gold silicon, the Young's modulus is actually larger than the Young's modulus of silicon. So in that case, your frequency is actually going to increase, going from here to here. As I said, we are looking at new trimming locations. Northrop Grumman, or they're fabricating their device, they have those little spikes here, and they can do their mass modification either on the top or on the bottom. In our case, what we discovered is that by looking at eutectic trimming, we can actually have two different locations where we can do our trimming. We can either do it at the rim, because here there is strain energy, or we can do it at the post, because there's strain energy here. So if, for example, you look at different modes, for example, the M=3, M=4, M=2, M=3, M=4, and so on, that Cornell just described, you can see that M=2 has actually a strain energy peak at the post that you can see in color here, whereas M=3 had almost none. If you really zoom in, you'll actually see a little peak, and they have the strain energy higher. So if we do our trimming technique, we can actually do mass modification at the rim, and we can also do stiffness modification at the bottom, and hence we have a larger trimming range than what people had before. Now, having strain energy is not everything for gyroscope trimming. You actually need a little bit more. If you look at the M=3 mode, you can see that there's strain energy all around, but it's a bit difficult because you need to add a trimming material on top of your device. So if you have a shell and need to put gold vertically, it's pretty difficult to do in fabrication. Also, you can see for the rocking mode, for example, the strain energy is at the bottom. So it's of a better access for a laser. The laser just comes on the top, where the M=3, you would need to have a laser to come at an angle to be able to touch that region. But what you can also observe is that the strain energy pattern for the high frequency and the low frequency mode is actually very similar. So if you do any modification for this mode, actually you're going to do the same modification for this one. So if you have strain energy, but they have the same pattern for the high frequency and the low frequency, so for the drive mode and the sense mode, then in that case, you're not reducing the frequency split. What you're really doing is shifting both modes without ever looking at the frequency split. Now, if you look at the M=2, it's a bit different. You have strain energy at the bottom, which is a very easy access for the laser, but it's also patterned. This is a close-up view of the strain energy pattern at the post. You can see that we have red colors up to blue colors. And these actually are the strain energy. And if you do any modification here, you can have more effect than if you did any modification of the stiffness at this location, for example. But also, if you look, this is the pattern, the strain energy for the high frequency mode, and this is for the low frequency mode. And if you do any modification at this location, you can see that this location will have no effect. So what this means is that you can bring the high frequency mode and you can shift it without touching at the low frequency mode, or in a manner that's not very important. But similarly, you can look at the low frequency mode and you can actually shift it because here there's no effect. So you can either move the high frequency or the low frequency. So in the slide before, I told you that gold has the capability, when you do a gold silicon eutectic, to increase your frequency. So if you were to use the low frequency and to use gold, you would need to melt the gold at this location, and at this location, and at this one, as I'm showing here, to be able to bring the low frequency mode to the high frequency mode. But if you were to put aluminum on the bottom of your device, then you actually have to use this pattern. So our technique can work up, so it can shift frequencies upwards and downwards. But we can only do it in one direction for one given metal. So if we use aluminum, it has to go downward. So the relative positions of the trimming are different for aluminum and for gold. And also, last point, if you're going outwards, farther away from the post, you have less and less effect. And finally, you have the coarse effect here and the fine effect here. And you can see that they are located at 45 degrees apart. So if, for example, if you're here, the next location will be at a 45 degrees angle and not straight in that direction. Those locations are really great because it's really easy to find them. The only problem is when you have a gyroscope, you don't see them. So you need to find them. There are different ways, but one easy way is just to have your laser go around your device and just scan. And trying not to melt too much, just trying to get your result and pattern. So if this is like a simple animation to show you that you can find easily your good spots and also your bad spots, and then you remember them, and then you come in a second scan and you only go to the locations where the frequency split actually went down, was reduced, and you put more energy, more power to get the most effect. Also, once you find those locations, the locations, I didn't draw them, but they are between the green and the red, are locations where the frequency split actually didn't increase or didn't decrease. There was no effect on the frequency split. What's important is that those locations, if you melt gold or aluminum there, what happens is the frequency split doesn't change, but the orientation of the modes does change. So if, for example, your mode is not exactly aligned on your electrodes, by using those locations, you can actually move your results. But I don't have any result in those slides. I have them in the paper. Here is a simulation in COMSOL where I created a frequency split of 41 hertz. And you can see here that I'm modifying the stiffness, so the Young's modulus in this case. And you're going to find that there are 4 locations where the frequency split went down in an important manner. Those 4 locations correspond to the 4 locations in red that you could see around the post. Also, you'll see that sometimes the color becomes red, and they're at the 45 degrees location, and this corresponds to the other color, the blue color. So what's really important is that, you can see them here, right? That the frequency split increases. So you have to stay as small as possible on those bad locations. You find them, you don't touch them. You move on until you find your good locations. And since we know that they are at 45 degrees apart, what you can do is you can start going around the post until you find one location, and then by when you find one, you know the others are at 90 degrees or at 45, so you don't have to actually go on them. So I'm presenting the results when we went from 40 to 0.24 hertz. This is our provision, what we expect to be the quality of our technique with respect to other techniques. We don't have any experimental results so far, and we're working on them, and we're expecting to have those results. We are at low temperature, and we expect to have a higher trimming resolution compared to mass ablation. So to give you time for some questions, I'm hurrying up. And conclusion, we're looking at a new trimming method that is digital and that is complementary to mass trimming. And our future work is going to be to prove this experimentally. Thank you. There are 37 seconds.